So looks like we have a small group today. So I did actually set it up so that if we decide we want to do a breakout group today, we can. So I think we'll wait and see how things go. And if there's a question that looks like it might be good to have a breakout group, then we can do it, especially since we have a bit of a smaller group today. So does anybody have any questions, any quick questions about anything? I'm sorry, like I said, I'm sorry about the way the sapling marks things. That's just, for some reason, they won't give back marks for watching pre-lectures. And like I said, I've asked them to fix it. And so hopefully they will fix that eventually. But that's, like someone else said, missing one set of pre-lectures is a very tiny part of your mark. So I wouldn't worry about it. I doubt it'll make any difference. Yes, moment of inertia is smaller when mass is closer to the axis of rotation. That's correct. The last I checked on the marking of the written test, last night she was only about 40% done. So maybe by the end of the day, but I still have to look at them and scale them. So it's more likely going to be Monday before you see the marks for the written part. Other questions? All right, we'll tell you what, we probably should get started on the physics for today. So, and we were right in the middle of doing a problem when we ended last time. So let's switch over to the PowerPoint. Here we go. And I do quite like this comic before we go on to the physics. It's kind of a sweet comic. Which also has a physics theme about angular momentum, which is going to be one of our topics for today. And it actually is very specifically about what's known as conservation of angular momentum, that the amount of spin something has, if the net external torque is 0, will remain the same. So, and we'll see how that works a little bit later today. So, but before that, we're going to look at this problem. So we started on this problem on Wednesday, and we did the first part. So this is a kinesiology example where we have a muscle that's holding an arm horizontally. And we first we figured out how much torque the muscle could produce, the maximum torque for its maximum force, which is the 1500 newtons. And now we're working on the second part of the question, which is how much force does the muscle exert to support the arm in a horizontal position if the mass of the arm is 3 kilograms and its center of mass is located 0.15 meters or 15 centimeters from the elbow joint. Okay, so we're going to share our document camera again. Hopefully this will work this time for you guys. Okay, so here was our drawing that we did last time, right, where we drew in all the forces acting on the arm, and we drew in our X and Y axes here, as you can see. So, and what we're going to do now, remember what we're trying to figure out is that force F, okay? And one thing we did talk about last time was how we actually had to also include a joint force, because you need the net force to be 0 as well as the net torque, and there needs to be a force to the right to balance the left component of the force F. Okay, so now we're going to go through and actually start writing down the sum of the forces. So let's start with the sum of the forces in the X direction. So there's only 2 forces with X components. It's our force F and our joint force. And so one thing we don't have yet is an angle for our joint force. So I think just to draw it over here, again, since I didn't leave any room, I'm going to call the joint force Fj, and I'm going to call that angle theta. Okay, because that's actually also an unknown. We don't actually know what theta is, and we don't actually know what Fj is. Okay, but we're going to try and solve for those as well in a minute, just to show you how everything works. Okay, So basically now we know what are our x components. Well, Fj has an x component, which is just Fj cosine theta. And then F also has an x component, a negative x component, and that angle is 30 degrees. So we have minus F cosine of 30 degrees. And we know that that has to add up to 0 because we're in static equilibrium. All right, so now we can do the y components. All right, so now all three forces have y components, right? So we have F sine theta, that's a positive y component, sorry, F sine 30, right? Okay, and then the joint force has a negative y component. Okay, so that's minus F joint sine theta, right? Okay, so we're just doing our force things that we learned how to do previously, our vector sums, and then we also have a negative y component coming from the weight, right? So we have a minus mg, and that has to add up to 0 if we're in static equilibrium. Great, so that's our forces adding up to 0, which is important. And now we need to do our torques. Okay, so this is our new quantity, torque. Okay, and now we have to, if you're going to do torque, Fj represents the force of the joint on the elbow here. So it's the upper, it's sort of the upper bones on the lower bones at the elbow. Okay, there has to be a force at that joint there to make things balance. So now for torque, okay, first thing you do when you're trying to figure out torque is you have to choose an axis. Okay, and so we're going to choose our axis to be the elbow here. Okay, and now that's actually really important because now when we try to figure out what's going on, okay, you'll notice that one of the forces, the F joint, acts right at the axis. And because that force acts at the axis, its lever arm is 0, so the joint force does not exert a torque. So it's just the other two forces that exert torques. And then the other thing to notice is that our two forces, the F and the weight, exert torques in opposite directions. The F here is going to make the arm want to rotate counterclockwise, so that's a positive torque. But the weight is going to want to make the arm drop or rotate clockwise, and so that's a negative torque. So this is where the signs become important. Okay, so, and just like we've been doing before, okay, I'm going to use our expression that torque is F perpendicular times R. Okay, I'm going to use it that way because it's easy to figure out the perpendicular force, right? For example, the perpendicular component of F is just F sine 30. All right, so I'm going to have F sine 30 and then times the R, and the R is how far away F is from the axis, and that's our 0.030 meters. Okay, so that's the torque for the force F. Okay, and now we just need to do the torque for the weight. And that's going to be minus the magnitude of the force, which is mg. And that is the perpendicular, because that is the perpendicular force. It's already perpendicular. And then we just need the distance r, which for the weight is our 0.15 meters. And that has to add up to 0. All right, so that's balancing the torques. The torque caused by F and the torque caused by the weight. All right, so now I'm going to take our picture away here to make our lives a little bit easier. All right, and so one thing you might notice right away is we do actually know the weight. Okay, we know m. So we can actually solve for F just using the torque expression. We have everything we need here. Okay, so I'm just going to simplify this a little bit. What do we have if we simplify that expression, right? So we just put this on the other side of the equation and divide by our sine 30 times our 0.03. So we just have mg times 0.15 meters over sine 30 times 0.030 meters. Okay. And it turns out this is exactly equal to 10. So this is just 10. So those numbers, 0.5 divided by 0.03 divided by sine of 30, which is a half, is just 10 times mg. And so we get the magnitude of the force is 10. We plug in the mass of the arm, which was 3 kilograms, and we plug in our g, our 9.81 meters per second squared, and we get about 294 newtons for our force. Okay. Yeah, so torque counterclockwise is positive. That's correct. Okay, so that's how you would figure out the force, F. So you could just stop there, because that's all they asked for. Okay, but I thought it would be useful for you guys to figure out not just that, but figure out what's Fj, what's the joint force, and what's theta. All right, we can also figure those out, because now that we know what F is, we can go back and use our other equations. Okay, for example, we know that if we use our y equation here, okay, we know that, make sure I do this right, that, so using the y equation, we know that Fj sine theta is equal to F sine 30 minus mg. We know that that's true. Okay, and then we can plug in all our numbers, 294 newtons, sine of 30 degrees, minus our 3 kilograms, right, times our 9.81 meters per second squared, right, and we get about 117.6 newtons. Okay. All right, and that's Fj sine theta, right? So that would be the basically the y component of that force. Okay, and then we can find the x component of the force, which is Fj cos theta, right? And you can see up here it's just equal to F cos 30. And so that's our 294 newtons times the cosine of 30, which is about 254.6 newtons. I'm not being super careful here with sig figs, but you get the idea. Okay, and then you've got your x component and your y component, and so now you know how to do the rest of this. So I'm just going to write down the answer, but basically you've got, they're both positive. Okay, so we assume the direction correct, that both of those, okay, were like that. Actually, you have to be a little bit careful, because technically it looks like this. This is the size of the y component, but the y component's actually downwards here, right? Okay, so so it looks something like this. So the x component is 254 point, oops, that's messy. Let me write it again. Actually, you know what, I'm going to do it on the next page, because we run out of space there. Okay, but that looks something like this. Okay, so this one is 254.6 newtons. That's our x component. Our y component was 117.6 newtons. Okay, this is our theta, and this is F joint there. Okay, and then if you actually do your Pythagorean theorem and you play around with the tangent, just like we always do with vectors, you can show that the magnitude of F joint is about 280 newtons. And the theta, the angle there below the horizontal, is about 24.8 degrees. Okay, so that's how it would work. Okay, so if there are any more questions on that one, I can't find my original picture of this. Here it is. Okay, So that is basically, so we just solved for this force here. Okay, the force at the joint. Okay, do you want the other page up? Sure, I can put the other page up for a second. I will post these. Okay, but here's the other page up for a second. Okay. You're welcome. And like I said, just be careful here. I'm solving for the size of the y component here, right? Technically, right, the y component, as you can see up here, is negative. Okay. I should do, okay, the problem with doing lots of problems like this, there's two issues. One is it's very time consuming. And honestly, two, it's not the best way for you guys to do physics. Okay, to learn physics. The best way to learn physics is to do them yourselves. Okay, so I'm willing to do a few of these, okay, but I can't do a lot of these because it's really pedagogically not the best way to spend our time. All right, so I'm going to go back to the original question now. Yes, there will be more sapling chapter 8 problems to do in the next homework assignment. No, you wouldn't have something this long. You might have, the first two parts were less long, okay? So, but not the third part, because that's a bit longy. Torque is 0 because it's not rotating, exactly. So this is static equilibrium, and one of our conditions for static equilibrium is that the net torque is 0. Okay, so now we're gonna move on, because we do have one more chapter 8 quantity to look at, and that's our angular momentum. All right, so in the pre-lecture, they talked about how you can figure out angular momentum for two different possible scenarios. The first possible scenario is the angular momentum of an object that's moving in a straight line. And it's hard to believe that an object moving in a straight line has an angular momentum, but if you choose an axis point, like they've drawn here, if you choose an axis, in a way, you can think of it as it goes by. So as this particle goes flying by, in a way, it's sort of rotating about the axis. It is moving relative to the axis, at least. And in this case, the angular momentum here, and I'm doing the magnitude of the angular momentum, is the distance of the object from the axis point, r, times the perpendicular component of the momentum. Okay, so it's the component of the momentum perpendicular to the line from the object to the axis, right? And you can see that basically r is going to change, right, as your object moves along, and p perpendicular is going to change as you move along because your phi is going to change. So this is a quantity where those things are changing depending on exactly where you are. Okay, so you have to be careful about defining the angular momentum at a certain point in time here. Okay, so that's, and we probably won't do a lot with objects moving in straight lines in this course. We're going to do more with angular momentum of rotating objects. So rotating extended objects, like for example, our ice skater here. So here's an ice skater who's rotating. So this ice skater has a moment of inertia. They're rotating with an angular velocity omega. And the angular momentum of a rotating object, which we're going to use, again, L for, all right, is the moment of inertia times the angular velocity. Okay? And the plus or minus sign of this quantity is going to depend on the sign of the omega. Okay, the sign of your angular velocity. So you're going to have to pick a viewpoint. Usually with something rotating on the ground, our viewpoint is from above. So you imagine looking down from above, looking at the rotation, determining whether it's clockwise or counterclockwise from above. And clockwise then would be our negative angular velocity, and counterclockwise would be our positive angular velocity. Okay, because sometimes in these cases, those signs will be, often they will be important. We won't just be looking at the size of the angular momentum, but also which way the object is rotating. Okay, So sometimes you'll see angular momentum defined as a vector. We don't do that in this course, though you can talk about an angular momentum vector pointing along the axis. I will draw it that way in a minute, just because sometimes it's useful to draw it that way. But typically, we won't worry about the vector nature of angular momentum here. So what I thought we would do is we would do a question about angular momentum. So let's start this going. We've only got 3 choices. A, B, and C. Okay, so let's have a look at this question. So we have a thin rod of mass M and length L, and it's rotating about an axis through one end. Okay, so it's like you took a pen like this, and you rotated it about one end. Okay. A second thin rod with twice the mass, but the same length as the first rod, is rotating about an axis through its center. So it's like you took your pen and you rotated it around its center. Okay, so the first one is going about the end. And when you go about the end, your moment of inertia is 1/3 ml squared. But when you go about the center, your moment of inertia is 1/12 ml squared. It's smaller for the same m and l, because it's easier to rotate about the center than about one end. Because about one end, you've got more mass far away from the axis. And the question is, which rod has a greater angular momentum? The rod rotating about one end, the rod rotating about its center, okay, or they both have the same. And one thing you have to be careful here is that the second one, right, the formula, right, has a 1/12 in it, but it's got twice the mass and twice the angular velocity. And this one, you'll probably have to do a little bit of math to figure it out, at least with variables, right? Symbolically. All right, I think we're going to do about 10 more seconds. It's still taking people a little while to answer, but why don't you go ahead? If you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. So let's see what everybody thought. So what did we get? So the largest group are going for C, that these two objects have the same angular momentum. Here we're looking at the size of the angular momentum. But there's still a reasonable two groups for A and for B. All right, so I think we should have a look at this one and see how it works. Okay, so what we're going to do is actually go through and figure out the two angular momenta here. And like I said, this is the size of angular momenta. The sign, it depends on whether it's clockwise or counterclockwise. Okay, so this is how we calculate our angular momenta for these two objects. So for the first object, okay, we take the angular momentum, so we take the moment of inertia times the angular velocity. Okay, we know that the moment of inertia is 1/3 ml squared and the angular velocity was omega. Now for the second object, okay, we have a moment of inertia of 1/12 ml squared, but the mass this time is 2m, so I put a 2m in there for the mass, and the angular velocity is 2 times omega, and so you get 2 times 2, which is 4, divided by 12, and 4 divided by 12 is just 1/3, and so you end up with exactly the same value, that is 1/3 ml squared times omega. So these two objects actually have the same size angular momentum. So that's how you would figure out something like that, right? Where these formulas, these moment of inertia formulas, are things that you should have on your cheat sheet so you can look them up. But I'll probably typically give them to you like I did here for a test. Okay. So that's the quantity angular momentum. And one of the reasons this is a really important quantity, those of you who are chemists have probably run into angular momentum a lot because it's something that defines electron orbitals and atoms because of what's known as spin. Okay, and we won't deal with that so much here. Okay, we're going to look at macroscopic objects that spin. Okay, and so we're going to look at the one of the other fundamental laws of physics. We've seen conservation of energy, we've seen conservation of linear momentum, and so this is conservation of angular momentum. And this law says that if there is no external torque on a system, then the angular momentum of the system is conserved. And remember, this is for a system, so a system could have more than one rotating part. Okay, so, and this is what it looks like mathematically. So if the net torque acting on a system, external torque, okay, is 0, then the final angular momentum, LF, equals the initial angular momentum, LI. Or in terms of a large rotating object, it's I final omega final equals I initial omega initial. And so one place that's a really nice illustration, and they did this in the pre-lecture too, is what happens when ice skaters change their moments of inertia by pulling their arms and legs in and out. Okay, when they put their arms out, they increase their moment of inertia, and when they pull their arms in, they decrease their moment of inertia, and that has an impact on their angular velocity. And so I'm going to try and hopefully you'll be able to hear this video. It's kind of a nice description of what happens.
Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When a skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Anyway, so there's a nice illustration of how conservation of angular momentum works. So this is the classic example. So any questions about that? So I thought we would try a question ourselves then. So here is our next poll question, if I can get this to go. Oops, there it is. Poll question number 2. So this is another demo, which I wish I could do in class for you, but this is a hard one to do at home. So I thought we'd just have a question about it instead. There are some nice videos of this one, which I didn't manage to bring one up for today, but I think what I'll do is I'll put one in Canvas for you guys to see afterwards so you can see this in action. You may have done this in high school too, this one. This is kind of a fun demo. So some of you may have seen this before. Okay. But so the question is, you're holding a spinning wheel while standing on a stationary turntable. Okay, so there's this guy and he's standing on a turntable. The turntable is not rotating. Okay. And what happens if you suddenly flip the wheel so that it is spinning in the opposite direction? Okay, and so what I've done here is drawn a little arrow to sort of represent L upwards, and the idea is he's going to flip it, okay, so that it goes from L upwards to L downwards. Okay, so if you're looking from above, it's going to go from counterclockwise spinning to clockwise spinning. Okay, and that's sort of what the arrows are supposed to represent. Okay, so it's going from counterclockwise to clockwise. Okay, and I'm going to have something is going on YouTube here. I have to stop. So go ahead and try and answer that one where I figure out why something is making a noise here. Oh, it might be that someone has their microphone on. Okay, I think I might have just showed you guys the answer, didn't I? Oops. Okay, that's all right. All right, guys, I do that every once in a while. I show you the answer. So, all right, you know what? Since I've showed you the answer, I think we're going to bail on this one. So go ahead. If you didn't see the answer, okay, which I accidentally just showed you, then it doesn't matter anymore. So let's go ahead and yes, well done, everybody. So Friday gift, okay. So let's try and explain why is the answer start to spin in the same direction as the wheel was spinning. Why is that the right answer? Okay. So yes, occasionally I am a silly prof. That is very true. Okay, why is that the same? So when you go from this to this, okay, what exactly is happening? Okay. Well, this is what's happening. So the total angular momentum of the system is plus L upwards, okay? And if the wheel is flipped to have minus L, so the system started with plus L. If you flip the wheel to minus L, you and the turntable must gain a plus 2L upward so that the total angular momentum remains constant. Okay, so the idea, in a way, it's kind of like a vector addition. You've got, originally you had an L, a plus L, okay, but you flipped to a minus L for the wheel, and so the person in the turntable have to have a plus 2L to compensate, so that when you add that plus 2L to minus L, you end up with what you started with, okay. So angular momentum is not a vector technically. I mean, a lot of people define it that way, okay. I'm just drawing it this way because it's a good way to picture what's going on, because it's hard to picture the rotating. Okay, but in this case, like I said, the easiest way to do it is to look at it from above and think about the clockwise and the counterclockwise rotation. So originally, if we go back, okay, originally the wheel had a counterclockwise rotation. It switched to clockwise, which I'm representing as a down vector. Okay, because it switched to clockwise, the person, and the turntable have to have a larger counterclockwise rotation, okay, to balance it out so that your net angular momentum has not changed, okay? So it looks kind of like that if you treat them like vectors, but like I said, I'm just using the vectors to represent clockwise and counterclockwise spin, because there's not an easy way to draw that otherwise. So questions on that? All right. So if you do have questions, Ricky is here to answer your questions, as you've seen, okay? But what we're going to do now for the last few minutes in class, the last 14 minutes that we have, is we're going on to chapter 9. Okay, so that was the last topic we're going to look at in chapter 8, was angular momentum. And so now we're going on to chapter 9, which is all about stress and strain. And the first topic in chapter 9 is something we've already run into, which is called Hooke's law. So we've already seen that if you have a spring of some, say, length L0, and you want to stretch the spring, that you have to pull on it, and the more you want to stretch it, the harder you have to pull, okay? And say you want to stretch it by an amount delta L, okay? Then the pull you have to exert, okay? So this is the force on the spring. This is not the spring force, it's the force on the spring, okay? Is equal to a constant called the spring constant times the change in the length, okay? So that's something we've run into before. So it turns out that most solid materials, all solid materials, essentially can be thought of as springs. And so if you have like a rod of metal or some other material and you pull on it, okay, with one end fixed somehow so that you've got the equal and opposite F's on either end, so it's not accelerating, it's at rest, okay, you can cause it to stretch. Okay, this is a great over-exaggeration, this picture. You would not get this much of a stretch, okay, in real life, all right? For most materials, you might get this much stretch for something like a rubber band or a bungee cord, okay, but for a piece of metal, you wouldn't get this much stretch, okay? And how much stretch or how much force you need to make it stretch depends on the effective spring constant for the material. And the spring constant, K, depends on three things. It depends on a constant we call Young's modulus. It depends on the cross-sectional area, okay, of the material. Okay, so that's the area perpendicular to the length. And it depends on the initial length of the object, which we're going to call L0. And you can see that K is proportional to the area. So the bigger the area, the bigger the spring constant, the harder the pull. It's inverse to the length. Okay, so the bigger the length, the smaller the spring constant, the easier it is to pull, okay, a certain length, okay. And then Young's modulus, as we're going to see, we'll see some values for how big Young's modulus is. So you can basically take that spring constant, plug it into your formula F pull equals K delta L, and then if you rearrange it, basically divide both sides by that area, you get something that looks like this. That F over A equals Young's modulus times delta L over L0. And we call this Hooke's law for a solid. And we give the different parts of this equation names. So this quantity, the force per area, we call the stress. So this is the stress that you're exerting on your object. And it's basically just the force per area. So sometimes you hear people talk about stress fractures. Stress fractures are caused by a force, right? Acting on a bone, causing it to fracture. Okay? And then the other quantity here is delta L over L0. We call that the strain. And it's essentially the fractional change in length. It's delta L, how much the length changed, divided by the initial length. Okay, so like if something was 10 centimeters long and it stretched by 1 centimeter, then this would be equal to 1/10. and if you multiplied that by 100%, you could say it stretched by 10%, say. Okay. So we're going to see that basically, so Hooke's law for a solid says that stress, so the stress applied to an object is equal to Young's modulus times the strain. So there are different types of stress and strain, as you saw in the pre-lecture. Okay, there's what we call tensile stress. Okay, where it gets its name, it's the same root as tension. Okay, and tensile stress is when you pull on an object and it stretches, so it gains in length. Okay, and again, for tensile stress, you use the formula we've already seen. Okay, that Young's modulus is the stress over the strain. Okay, but you can also have what's called compressive stress. Okay, which is when you push in on both ends on an object and the length decreases. All right, and what we're going to see when we look at a table of some of these values next time is for some materials, the Young's modulus, or the modulus of compression versus tensile stretching, is the same. And for some materials, it's not the same. Some materials react differently when you compress them than when you stretch them. Okay. So yeah, that area, just to go back, that area is the cross-sectional area of the rod. Yeah, sometimes Young's modulus is also written as E. That's true. Okay, so you'll have to just be careful. I'm gonna write them as Y. Okay, but this is one place where people use different variable names for the constant. Okay, the last kind of stress and strain, or this is not the last one, but this is the last one we're gonna look at today, is this kind of stress that we call shear stress. Okay. And I realized I forgot to label it for you, that this is shear stress. Okay. And so what happens here is that you've got an object and you're basically you're pulling at the top on one side and the bottom on the other side. And so it basically deforms in a way. Okay. I think the best way to say this, okay, but this is, like I said, this is shear stress. Okay, but essentially it's like you had an object and the bottom was fixed and the top was able to slide relative to the bottom. Okay, and in the case of shear stress like this, okay, the quantity you care about is how far over did the top move, this quantity x, relative to the bottom. Okay, so if you were to basically drop a vertical down from the edge of the top after you've exerted this force on the top, this force we call F parallel, okay, how far over did that top move relative to the bottom? And the thing we really care about is the ratio of x to h, the height. Okay, where h basically is the distance between where the top F parallel is applied and where the bottom F parallel is applied. Okay, and we have a shear stress constant here, S, okay, which is equal to, very similar to what we have for our Young's modulus here. It's a ratio of force per area. So in this case, it's the parallel force per area, cross-sectional area. Okay, be careful though, in this case, the area is the top area. Okay, so you can see an A sitting there. Okay, this area is the top area, whereas the other area was the area, cross-sectional area of the end. Okay, and then that's divided by x over h, okay, which is the strain in this particular case. Okay, so that's another type, and then there's one more type, which we'll talk about next time, okay, and where S then is called our shear modulus, because this is our shear stress. A is typically, usually we talk about a symmetric object, so A is the top and the bottom, okay. So what was the question? Which one was cross-sectional? So the cross-sectional one was the previous one. So we go back, okay, when you're doing tensile or compressive stress, then A is the cross-sectional area. But when you're doing shear stress, it's the top area. Okay? Other questions on that? we're going to do an example of this next time, but I thought we would end today with one of my favorite clicker questions, which is this one. So we'll start this one going. Okay, so here we have a sheep, okay? And you can see the before on the left and the after on the right. And the question is, what type of stress has this sheep undergone? We're all under stress. This poor sheep is under stress, okay? And the choices are, or maybe he's not under stress. So the choices are tensile, compressive, shear, or none of the above. The sheep's not stressed at all. All right, I think we're going to do 10 more seconds on this one because it looks like most people have voted. Okay, 5, 4, 3, 2, 1. And so we have lots of consensus here. Almost everybody is voting for C. Not everybody, but almost everybody is voting for C for shear stress. We'll end the poll. And that is correct. This is shear stress. Okay, how do we know it's shear stress? Because his feet are still in the same place, but his top half has shifted sideways relative to his feet. So this is an example of shear stress. Don't ever do this to your sheep. This is the wrong kind of shearing for your sheep, right? But just to see, this is this kind of stress, okay, where the top part is sliding relative to the bottom. Okay, so that's all I was going to do for today. So I'm happy to answer some questions on anything now or earlier. If not, have a good weekend, and I will see you guys on Monday.
Hi, Professor.
Yeah.
I was wondering when the next sapling assignment will be posted.
Probably this afternoon.